Bismillahirrahmanirrahim. Hello everyone. I hope you are doing well. My name is Azmat Ali and I welcome you all in class of elementary number theory by David M. Burton. In the last lecture we discussed question number 20 that is actually related to properties of GCD. Continuing the pattern of properties of GCD, in today's lecture, inshallah, I will discuss some more results which are actually the properties of GCD. One of the important things that you should know, the problems that I will discuss today in David M. Burton book, these problems David did not explicitly refer to as a properties of GCD. These problems actually are available at different pages in the form of theorems, examples, and questions. But I have collected all of these problems and refer to them collectively as properties of GCD. Actually, these problems are properties of GCD. So this will be convenient for the students or learner when we use these results in our next questions. That's why I am telling them as properties of GCD. So let's discuss these properties. The first property is we have to show that the greatest common divisor of two integers a and b is unique. To prove the uniqueness, we suppose on the contrary that GCD is not unique, and let C and D both are the GCD of A and B. Firstly, we consider D as a GCD. Now, as D is a GCD of A and B, so by definition of GCD, which says D must divide each of integer A and B. When you take D as a GCD, then C will be considered as common divisor. So in this case, when D is GCD, C is a common divisor. So that's why by definition of common divisor, C must divide both A and B. And also, as D is the greatest common divisor and C is just a common divisor, so by definition of greatest common divisor, C must divide D. Likewise, when you take C as a GCD and D is just a common divisor, then D must divide C. By the theorem of divisibility, which says that if A divides B and B divides A, then it must be that A is equal to plus minus B. So here, by using this result, we can write C is equal to plus minus D. But C and D are positive integers because both are the greatest common divisor, and greatest common divisor is always a positive integers. That's why we will neglect the case of negative integer. So this becomes C is equal to D. And this shows that both of the numbers, both of the integers, both of the GCD are same. Hence, our assumption that C and D are two different GCD of A and B is wrong. Hence, GCD of two integers is A and B is unique. Next, the property, very interesting property. This is Bezout lemma. This says if D is the GCD of AB, then show that D is the smallest positive integer that can be expressed as a linear combination of A and B. This property I have already discussed in my previous lecture. So you can see the proof of this property from there. This is property number 3, and this is actually theorem 2.7 in section 2.4. And this is very important property. This property says if k is any positive integer, then GCD of k into a GCD of ka and kb is equal to k times GCD of ab. In other words, we can say that if we multiply a and b with the same integer k, then we take common k, and the result is product of k and GCD of a and b. For example, if we apply this result to some particular example, like I say, what is the GCD of 3 and 6? The GCD of 3 and 6 is now, this is 3. This 3 is the greatest common divisor that divides both numbers. Now, if we multiply both of the numbers by some number like 4, 4 into 3, 4 into 6, this becomes GCD of 4 into 3, 12, 4 into 6, 24. Now, GCD of these two numbers, 12 and 24, is 12. On the other hand, if you apply this result says that you can take common 4 from there. This and remaining is GCD of 3 and 6. GCD of 3 and 6 is 3. So multiply 4 with 3. This is also equal to 12. Now we prove this property in general. Uh, let let d is equal to GCD of AB. So by using the property number 2, that is the Bezout lemma, this d can be expressed as a linear combination of a and b. What does it mean by the linear combination of a and b? Linear combination of a and b means sum of product form. That is, d can be expressed as ax plus by. What is x and y? X and y are the integers, and a and b are the integers whose GCD we are interested to find. So d can be expressed as ax plus by. On the other hand, I have to find GCD of Ka and Kb, so multiply this expression by k on both sides. We have Kd into Kax plus Kby. These two numbers can be written as Ka times x, Kb times y. As the right hand side of star shows, this is also a linear combination of Ka and Kb. So by Bezout lemma, star turns to Kd is equal to GCD of K, Kb. What is Bezout lemma? Actually, the Bezout lemma says GCD is the smallest positive integer that can be written as the linear combination of this. So if we have a linear combination for some integer x and y, so this can be expressed as the GCD of Ka and Kb. This implies GCD of K, Kb is equal to K times D. What is D? D is GCD of AB. That completes the proof. I have a corollary related to this result. This corollary says for any non-zero integer k, GCD of Ka, Kb is equal to absolute value of k times GCD of AB. In theorem 2.7 or property number 3, here we have taken k as a positive integer. But in the corollary we says if k is negative, then this property also holds. But in that case we will take absolute value of k outside of GCD of AB. So to prove this corollary, we will just use the concept of absolute value of function. The k absolute is equal to positive k if k is greater than or equal to 0. This is equal to minus k if your k is negative. So it means the absolute value of k has two values, plus minus k. In above the case of positivity of k we have discussed here. So now we will show the result also hold for negative k. So it is sufficient to consider the case in which k is negative. So when k is the negative, then its absolute value will be equal to minus k. But you know absolute value is always positive, so k absolute is greater than 0. Now consider the left hand side, that is GCD of AK and BK is equal to GCD of minus AK minus BK. How they are equal? By using the result. Uh, this result we have proved in problem 2.3, which says GCD of integer A and B and GCD of minus A minus B both are equal. So that's why GCD of AK and BK is equal to GCD of minus AK minus BK. Now can we write as minus A time K can be written as A into minus K. As K is negative, so minus K is equal to K absolute. So we replace minus K is equal to its absolute value K absolute here. So this becomes A into K absolute. Similarly, this becomes K into BK. Now as K is positive, so I can use theorem 2.7, which says if k is positive, then we can take k as a common from here, and this is equal to k times GCD of AB. So the absolute value of k is positive. That's why we can write it in the start. This becomes k absolute times GCD of AB. So the result hold for any non-zero integer. Property number 4. This is also very important property. This property says if D is a common divisor of A and B, then D is equal to GCD of AB if and only if GCD of the fraction A over D and B over D is equal to 1. In other words, this property says that if D is a some GCD of some if D is a GCD of some integer A and B, if you divide these integer by their GCD, then they becomes relatively prime. Mean to say their GCD becomes 1. For example, GCD of 3 and 6 is equal to 3. Now if you divide these two numbers by their GCD, we have the fraction 3 over 3, 6 over 3. 3 over 3 is equal to 1 and 6 over 3 this is equal to 2. Now what is the GCD of 1 and 2? GCD of 1 and 2 is clearly 1. So this property says that if you divide some integer A and B by their GCD, then it must be that their GCD of their fraction is equal to 1. In other words, their fractions are relatively prime. Here it may be noticed that these fractions is always an integers. A over D and B over D will not be in decimal form. This will be exactly a whole number or an integer. Actually, this is a question number 3 in problem 2.4. Let D is equal to GCD of AB. We show that the GCD of their fraction is equal to 1. So as D is the GCD of AB, so by definition of GCD, D must divide both of the number. D will divide A and D also divide B. So D divides A and D divides B. Now by using the definition of divisibility for D divides A and D divides B, we can find two integers m and n such that I can write A is equal to D time n and B is equal to D time n. I hope you have an idea of definition of divisibility. Now consider again D is equal to GCD of AB and substitute the value of A and B here. A is equal to D time m and B is equal to D time n. As D is a positive integer, so by using theorem 2.7 or property number 3, we can take D as a common from here and we can write it as D is equal to GCD of mn. Now again substituting the value of m and n from here our m is equal to A over D and from here our n is equal to B over D. So substituting m and n in the form of A, B and D. So this becomes A over D, B over D. And lastly, by cancelling out this D with this D, this becomes GCD of A over D and B over D is equal to 1. Conversely, we suppose that GCD of AB and B over D is equal to 1 and we show that the GCD of AB is equal to D here. Consider consider this number GCD of AB. We multiply and divide both of the number A and B with D, like as D into A over D, D into B over D. As D is a positive integer, so by using property number 3, we can take D common from here. This becomes D into GCD of A over D and B over D. But as GCD of AB, A over B, A over D and B over D is equal to 1. So replacing this is equal to 1. This becomes D into 1, D into 1 is equal to D, which is required to prove. Next, in the next lecture, inshallah, we will discuss question number 4, problem number 2.4, and actually I am again referring this question as a property of GCD, and this is very important question regarding your final exam also. So see you in the next lecture. Take care. Allah Hafiz.